Everyone, we are Group 55. Our project topic is chest X-ray disease diagnosis. Lung disease is officially verified as the top 3 life-threatening disease in the United States, following cardiovascular disease and cancer. X-ray has long been a preliminary advisory tool helping the diagnosis of many diseases throughout the world. How to help patients understand their X-ray image and how to use machine learning algorithms and big data techniques to analyze X-ray image sufficiently is what our group focuses on. We use Tri-Expert dataset, which consists of 224,316 chest X-ray images and 65,240 patients from October 2002 to July 2017. The data structure was divided into X-ray image, sex, age, will, and label of 40 diseases, and after research on dataset, our group trained 5 different models which are U1s, U0s, U multiclass, U self-trained, and U ignore. For the data pre-processing, we did grayscale data normalization and separate data based on female and age. This graph is an example of what our data looks like after data pre-processing.
Our deliverable was in 2 parts, the modeling part and the application part. The modeling part involved dataset analysis, data splitting, data augmentation, setting up the learning rates, hyperparameter tuning, training by GPUs, and model evaluation. Once we found a satisfactory model by iterating on those model parts, we were then able to use that for our application. Our application consisted of the machine learning model web API, which was used to expose the models developed, our backend, which Flask was using to provide data to the front end, and our front end, which was a D3 front end that visualized predictions made from that model. For our approach on modeling, we used convolution neural networks, which are a class of deep neural networks, and we applied them to the image set. We compared ResNet, DenseNet, AlexNet, VGG, and SqueezeNet and found DenseNet to be the most performant. Specifically, it was able to reach state-of-the-art results, having to tune less parameters on the classification datasets. Some of the tuning parameters we used included split ratios, which were originally 60,000 to 200, and we modified to 99 to 1 and 9 to 1. We also tried 1, 3, and 5 different epochs, and 3 different image sizes, 224, 128, and 64. We also used the SGD optimizer and used normalization using RGB and grayscale. And for the images themselves, we flipped the image, changed lighting, changed zooming, changed rotation, and changed warping to develop the model.
Here you can see these are the models that we trained, and if you want to find the file, they are located in a different folder in our code package. Firstly, in the first stage, we want to find the prototype for our machine learning model. So firstly, we want to experiment with different approaches against the multi-class labeling situation. We use 1, 0, ignore multi-class, and self-trained. The details can be found in our report. And as you can see, the training time for multi-class is the least, and also it reached a good accuracy level. So we stick to multi-class. Secondly, we want to choose which neural network we want to implement it in our final model. We experimented with DenseNet, ResNet, AlexNet, SqueezeNet, and VGG16. As you can see, that the AlexNet and SqueezeNet takes relatively half of the time than the rest, but their accuracy level is also much lower. So we choose to use DenseNet, which is taking moderate amount of training time and with higher accuracy level. So we have choose our prototype to be using multi-class and DenseNet. Then we want to finely tune our model by tune those hyperparameters such as split ratio and epoch. As you can see the result, we should stick to the original split ratio that is provided by the Stanford University, and the epoch should be 1 because if you increase the epoch, it will actually go into the overfit situation. Then we also try to experiment with different input resolution, which is, of course follows our intuition that if you use higher resolution image, it takes longer time to train, but the accuracy will also increase. So we stick to the resolution of the highest one, 224, because it takes moderate amount of training time. It's not overly too long. Then we also try to experiment with different optimizer, normalizing parameter, and also using data augmentation or not. As you can see that those experiments do not show much significant improvements in our results. Actually, it's making it worse. So finally, we have decided that our model would be using the highest resolution, Epoch 1, DensNet, and the other parameters are not taken. Here is the evaluation through our whole project. From our whole project, two cases that are worth our attention. Firstly, the worst performance. The worst performance happens when you use a SqueezeNet. It only takes 11 minutes to train, but as you can see, there is a significant decrease for every indicator disease prediction. However, for the best performance, it happens when we use the DensNet. It takes 25 minutes, but it's not too long, and you can compare it with the best performance from Irvin's paper, that there is improvements in every indicator, disease, the prediction level. So we can conclude that our whole project is successful in certain degree.
So we built a web application using Flask, D3.js, and basic HTML to show our result. The backend server will take the image passed by the client and convert it to the right shape and feed it to our training model for prediction, and send the result back to the client. So for see it more intuitively, we prepared a short demo here. At first, we run this web app. We still not be able to take it online, so we run it locally. And you can upload your image to it. Click the predict button, and the result will show up. Okay, so for the first one, this patient seems to have several diseases. You can check the feature image and symptoms of each of them. And for the second one, yeah, it's healthy, so we end up with a no finding message here. So to summarize, we created and trained a good performance chest X-ray disease prediction model based on a CNN DensNet. And then we successfully implement a full-stack chest disease diagnosis application based on that. We have learned a lot from this project, like how to training and tuning the model, how to using a distributed system to save computation time. This application is also not perfect. In the future, we could improve the accuracy by using new machine learning model or collect more data. The interface could also be more friendly. So thank you for your attention.